Welcome back. This last section of the chapter and the book is on impulse functions and convolution, and really introduces you to some further work with Laplace transform and other transformations. The convolution is a really interesting, complicated idea that can help separate out mixtures in the frequency space as an alternative to partial fraction decomposition, but it gives us a really neat intuitive idea or concept behind that separation. To start out, we define our convolution integral with this shorthand f star g, defined as the integral from tau equals 0 up to t, there's that u substitution, that tau variable again, of f of tau times g of t minus tau d tau. Now what this means is that we're going to integrate two functions where one's traveling to the right and one's staying still and one is traveling past it, traveling to the right past it. So we're basically overlapping two functions and seeing what comes out of that, what area comes out of that convolution of these two signals, in a sense. Here's an example of a convolution of two unit step functions. While the unit step functions are fairly basic, this gives a good visual for how the convolution works. For our first function, we just get the function in terms of the tau variable. And the second function, we replace t with t minus tau. Now it has minus b, that's fine. So we get t minus tau minus b. And we're integrating in terms of tau. Okay, so let's remember that unit step functions are binary. They're either 0 or 1. So this integral is really adding up zeros and adding up ones over the full intervals. Let's split up the interval in terms of when is it 0 and when is it 1. So let's assume that a is less than b. Make things simple. We could go through and prove the other case, but let's just keep that true. Now, for t between, and this is also assumed that we're between 0 and some other value. So our first interval is between tau equals 0 and a. And over that interval we get 0. We know that. And then we have the integral from from a to t of 1 times u, and I'll rewrite this, is t minus tau minus b, d tau. So we applied the binary nature of the first unit step function. Now I just need to figure out how the second unit step function works out. So we have the unit step function where tau is the variable, and to keep that in perspective, u of t minus b minus tau. And we know that the activation happens when tau equals t minus b. So we just need to figure out when's it off, when's it on. Well, normally if it was reverse of tau minus that, we know exactly the ordering and how it works. But since we've negated it, it's going to be the unit step function working in the inverse direction. So for example, here is u of t minus c. This is our c value. Whereas there is u of c minus t. Because u of t minus c is 1 whenever t is greater than c, giving us a positive value. If you negate the inside and you have t being greater than c, then you're subtracting and getting a negative value for u, and that makes it 0. So wherever the input is negative, the output will be 0. Whenever the input is positive, the output will be 1. Okay, and for this integral, t is a constant. It's a constant limit, and we're going, you can think of this as going from 0 up to t minus b, and then t minus b to t. So we break up our limit. Going from tau equals a to t minus b, and along that value we have a 1, and then the integral from tau equals t minus b on up to t, and along that value we have a 0. So that's gone. Okay, so now we've zeroed in. We know that the summation is only happening over the interval between a and t minus b. And so we integrate 1, we get our tau from a to t minus b. That gives us t minus b minus a. Before we graph it, let's think about this integral calculation a little bit more carefully. Since we knocked out the limits from tau equals 0 to a and the limits from t minus b to t, we are assuming a certain range of t values to fit in here. We want, first off, our t minus b to be bigger than a, otherwise we would have had 0. So for t minus b to be bigger than a, we need t to be bigger than a plus b. So that's the activation point for this convolution. And ironically, or perhaps is it unexpectedly, the solution to this convolution of 2 unit steps is in itself a unit step function, because this term, this t minus a minus b, is only defined for t that is greater than a plus b, which means that we have a 0 function that's switched on, and then that function is just a line. X equals t, that's shifted down a plus b. So now let's graph this on Wolfram alpha. First off, Wolfram alpha does not recognize the unit step function as a u, but it has 2 other letters which it does recognize that as. First is a capital H to represent the Heaviside function, but it usually converts it into the a theta, which is kind of odd. But if you wanted, you could replace the capital H with a lowercase theta, and it would hopefully recognize that as another Heaviside function. Okay, so now let's look at the convolution. Delete that back so the H's to remind me. And here is our graph. For a equals 1 and b equals 2, then a plus b is 3, and that's exactly where the line is activated. So before that, the line would extend down here, but because it's in the region of the integral that's below a, or I should say t minus b is below a, then it's 0 here. So I have a t minus 1 minus a unit step of t minus 3. That just means that we're turning on a 1 at t equals 1 and then turning it off at t equals 3. So that's one block. And the other block will turning on at 1 and turning off at 2. And so we have two unit blocks, or sorry, I should say, we have two step blocks that are being turned on and turned off by unit steps. One's a little bigger than the other. And when we overlap them, we should see that one, first, there's a little gap of 1 because they're starting at t equals 1. So when I reverse order, take a little time before it hits. And as the first blocks are interacting, we get larger and larger area until we finally have one block encased in the other for a full unit. And then the inner block escapes out the other side, and so the area diminishes down towards 0. I hope these visualizations are helpful for you to see convolution. I strongly encourage you to try just playing around with Wolfram Alpha to see what some of the other convolution shapes are based upon unit steps or perhaps even other functions.